Good morning, everyone. And indeed, today, this morning, I'll be focusing the discussion on structure. And as I threatened from my title, I'm actually doing a supermarket talk, and I'm sticking everything in the basket. In particular, I want to touch on quenching, environmental effects, and morphological transformations due to quenching, and connect at the end with the issue of what are we seeing in the growth of the sizes of the median size of the quenched galaxies. So let's start with the issue of quenching. So galaxies switch off, and we have realized in the last few years an interesting property of the fraction of galaxies which are quenched, and in particular separability of this quenched fraction with galaxy mass and environment. If you plot this, the fraction of quenched galaxies with galaxy mass, it doesn't seem to depend on environment, and if you plot it with environment, it doesn't depend on mass. This separability has led to the strong feeling that there should be two really distinct quenching processes that I will be naming environment quenching and mass quenching using the terminology of Peng et al. Paper, Simon and Ing's paper. But of course, such processes are being discussed at length and in detail for years. In particular, if we go to the fundamental mode of quenching that for just name purposes I'm calling mass quenching, again, we know that there are many ideas about what this mode of quenching might be that essentially acts independent, apparently, of environment. And here are just several of the ideas which have been mentioning: AGN feedback, halo quenching, and others, morphological or gravitational quenching. When we go to environment quenching, I think one important thing that we have realized in the last few years, there have been very nice papers out on this, is that environment actually means halo. That's what a galaxy sees. So environment quenching is pretty much thought to be an effect that affects galaxies when they become the satellites of another halo. And again, therefore, I will be calling this effect satellite quenching. For this particular environmental satellite quenching, again, many ideas out. This talk is not about trying to discuss these processes, but it's actually about discussing is structure affected by any of these processes and how. And given that there is this idea that they should be two independent processes, then the question I want to ask is, how does mass quenching affect the structural properties, and how does environment satellite quenching affect the properties of galaxies? So this is the main topic I'll go into, but before I start, I want to dump my own belief about how the universe works. And in particular, I just want to, 1 second, sort of stop on the fact that as we talk about these populations of galaxies, thanks to the wealth of the galaxy population that now we are working with these large samples, we have sort in our mind the definitions that we have learned to give in terms of our star-forming main sequence at any redshift that we have been able to sample. And then the quenched population being this population here would suppress the specific star formation rates with respect to the main sequence. But in my mind, having started 20 years ago with the local galaxies in the nearby universe, I don't want to forget, and I don't think we should forget, that when we come to redshift 0 and we talked about these quenched galaxies and the early type galaxies, actually we're seeing an important diverse population. And the diversity is set by this mass scale here, more or less at 10 to the 11, which happens to be the pre-constant m star of the mass function that we see with cosmic time and in environment. And below this mass scale, the early type galaxies are the famous very fast rotators, have steep cusps in their nuclei, have disky isophotes, have steep metallicity gradients. They have no other way of telling us that they suffered at the dissipative formation process. Above these guys here, above this mass scale, they have flat cores, they have the flat metallicity gradients, they have the boxy isophotes, they are the slow rotators. And I don't see how else we can make this property galaxies if we don't merge dissipation of the stellar systems. So this is my prejudice, and because this is my belief, when I'm talking about quenching and producing, therefore, from quenching early type galaxies, I'm talking of forming M-star spheroids with the properties of a rotationally supported dissipative system. This is the kind of discussion I want to entertain this morning, and I will start focusing on satellite galaxies in particular and on redshift 0 practically groups. I'm going to use the sample of our ZENS survey. Just want to say that the 3 papers that present the survey and all the data and measurements are these 3 here, and are the PhD thesis of Anna Chibinel, and that once and for all, I'm going to present just one plot and not many multiple plots, but all the analyses are done at constant mass, so stellar mass of the galaxy is kept under control. So the very first thing to say is that we in our data find what everybody else finds too. Again, lots of lovely work done on this before ours. Essentially, if you look at the fraction of quenched galaxies with the halocentric distance inside halos, a constant galaxy mass, as I've said before, this quench fraction decreases the more you go away from the center of the halos. Plenty of evidence from many works. What is very interesting is that this picture is no doubt consistent with the 2 processes that we have been having in mind. One that acts on all galaxies, independent of where they are, essentially, and one that instead is due to the fact that the satellite plunge into the halo and becomes satellite. So you can set a mass quenching level here in the outskirts, and just think that this excess of quench fraction is due to the environmental satellite quenching process. Well, very interesting, but then if you go and measure the fraction of quenched galaxies which actually have an early type morphology, this fraction is very, very constant with distance from the center of the halo. And so the morphological mix of the quenched fraction inside halos seems to be completely decoupled from the overall quenched fraction inside the halo. If we accept this picture that here is mass quenching that acts and this is the effect of satellite quenching, the fact that the morphological mix is identical must mean one of 2 things. Either that both quenching channels produce somehow the same morphological mix, or that there is no morphological transformation associated with the quenching. Again, in parentheses, this is not a weirdity of the ZENS sample at redshift 0. Don't want to go into the details of this other work which is in preparation, but if I take the Cosmos sample, use the Z-Cosmos group catalog out to redshift over there, 0.81, whatever I do in binding of mass and redshift with the galaxies, again, this is the quench fraction of early type satellites, pretty constant from the very center to the field, essentially, in the Cosmos galaxies. So this is really not just a feature of a data set. It's pretty much what the universe below redshift 1 seems to be doing. And so the first conclusion is the morphology density relation that is so well established is not a result of changes in the morphological mix toward the centers of the halo, but is a result of the fact that the fraction of quenched galaxies increases towards the centers of the halos. Now, there is, however, something which obviously disturbs us, and the fact that disturbs us is that I'm saying this, but of course we know that despite this morphological statistical outcome, when we go into the studies of the galaxies, the morphologies of the quenched satellites are systematically different than the morphologies of the star-forming satellites of same mass. And in particular, if we look at the distributions of bulge to total in the quenched satellites and in the star-forming satellites, same mass, and the half-light radii of these galaxies, well, we know very well that the bulge to total of the quenched satellites are much larger than the bulge to total of the star-forming satellites, and the half-light radii of the quenched satellites are much smaller than the half-light radii of the star-forming satellites. So this is certainly a problem. How big a problem it is It's very interesting that if we actually, this is where the interesting bit starts, if we bother to decompose in bulges and disks, both the star-forming and the quenched satellites, and now you have to bear with this horrendous figure with me, sort of thing. The bulge components of star-forming and quenched satellites are the gray things that you say, I can't see a difference, this is my point. And the disks, instead of the star-forming, are the blue, and of the quenched are this purple sort of bands here. And so the main point is that you don't see a difference in the bulge indeed, and neither do I. The bulges in quenched and star-forming satellites are very similar luminosities, very similar surface brightness profiles. And so if we think that there should be any growth of mass in the bulges associated with quenching, this cannot change these quantities because we find them the same. What changes indeed, as I've already highlighted by pointing out the profiles of the disks, is the disks. The differences are due to the differences in the disks, which have lower luminosities than in the quenched galaxies. So what does this really tell us about quenching and morphological star formation? Again, one thing that we know forever almost is that as we come to these late epochs, star formation in galaxies is really confined in the disks. So when we have a massive bulge, because these star-forming objects that we're seeing at this high M-star mass scales have already well-developed and dense central bulges, and we have a star-forming disks, here the blue lines, and the bulge quenched is in the center as the black line. And we quench this disk because it's where the star formation occurs. Well, by the time we quench the star formation, the stellar population are going to fade. And so as we quench star formation in a disk of a galaxy, suddenly, from then on, what we're going to see is a much higher prominence of the bulge component and a more and more irrelevant prominence or relevance of the disk component. This is really something we can't avoid, and the only thing we can discuss is how much this is playing a role. Is it enough to explain what we see? And, you know, order of magnitude, it is. I mean, it just takes a one-on-one exercise to say, you know, let's just parameterize the fading of the disks of the quenched versus the star-forming satellites. If we keep the bulge fixed at surface brightness, as we see in the data, and we just faint the disks, you know, for example, for a fainting of 1 magnitude, an epsilon of 0.4, you end up from having a sort of 0.4 bulge to disk that becomes a 0.6 bulge to disk. Again, a substantial increase in the bulge to disk ratio. So disk fading after the quenching of the disks at redshift 0 increases the morphological bulge to total, and because actually you are suppressing the relevance of the disk, also will decrease the alpha radii of the structure, and this without any change in structural mass in the stellar system. We can do something else because we have the data. We can actually say, well, can we see this in the data rather than with the 101 little exercise? Well, then what we do is we take the quenched satellites, and these are again the bulge to total and the half-light radii. We take their decompositions, so we take their bulges, we leave them the same because they seem not to change. We take their disks and we fade them. We fade them because of sudden stellar population quenching that then lasts for passive evolution that lasts for 1 gigayear or 3 gigayear. These are 2 incarnations of these simulations of disk fading. As you can see, they don't matter very much. What matters is that indeed, from the similarly to what I was saying before, this is absolutely enough to explain the distributions of the bulge to total that we're seeing in the bulge satellite. So does it all work? Obviously not, because I don't need to put here medians and any sort of statistical test for you to notice that we have a problem with the half-light radii. If you do this trick, the half-life radii of the quenched satellites do remain much smaller than the half-life radii of the fainted, uniformly fainted disks of the star-forming satellites. Well, there is something else that is giving us some hints, and is that if we now look only at the disk components again, Here is the central surface brightness within 1 kiloparsec, and here is the scale length of the disk. Color coding is like the one of before. So the magenta are the observed quenched satellites, the blue are the observed star-forming satellites, and red are the faked quenched disks of the satellites. Well, obviously, first of all, I want to notice that the central surface densities of the disks of quenched and star-forming satellites are pretty much identical. And here you can see that the problem is that the magenta points are concentrated very much as small scale lengths, and the blue points instead, the disks of the star forming are much more extended, of order of factor 2 on average than the scale lengths of the quenched disks. Obviously, if we do a uniform fading, the scale lengths in the blue points are not going to change, and so the red points are just going to be down, but are not going to cure this problem, this factor of 2 in the scale lengths of the disks.
Sorry, what pass band?
This is done in I band.
Okay.
And so, obviously, the simple fading may be missing something, and of course it's missing something. There are at least 2 reasons why the simple uniform fading with radius shouldn't work. And the first is that if we believe in an inside-out growth of disks, we should have radial age gradients that therefore motivate a differential fading with disk rather than a uniform fading with radius. And the other thing is that, you know, again, if disks grow inside out, the disks would be smaller at the time we quench them before we see them quenched today. So both these reasons motivate to go one step further, again, in an extremely toy, sort of Mattel toy model, nothing more. But if you think everything is exponential, the star-forming disks are exponential, and the quenched disks are exponential, they just have 2 different exponential scale lengths. Also, the fading with radius will be exponential. No need to go into the trivia. Let me just say that if we want indeed to reproduce half of a disk scale length in the quenched galaxies relative to the progenitor star-forming disks, then what we get is a scale length of the distributions of the fading, if you want, which actually matches the one of the original star-forming disk. And we get indeed very little fading in the center. That is just what we want given the data. And we get about a magnitude of fading at the scale lengths of the original star-forming disk. These parameters, if you had spectroscopic eyes, would have seen are precisely what we see when we decompose our disks and bulges, and from our measurements is totally consistent with 1 to 3 billion years of passive evolution. And so the conclusion is that if we are a little bit more physical about fading the disks of the star-forming satellites, we get the quenched satellite population at redshift 0 that we are observing without any need at all for any substantial mass growth in the central component or other any changes, structural changes to the central component. The second important point is that this again is consistent and supports the idea that we don't do any structural changes, so neither of the 2 quenching channels is going to affect anything in the stellar mass distribution. The third point, which I had already hinted before, if something quacks like a duck, maybe it's a duck, if nothing is changing the structural properties, neither of these 2 processes is changing the structural properties, and so from the structural perspective, the structural properties are acting in the same way, why not to say that they are the same process? We still have to keep in mind the famous separability I started with, but I'll come to that at the very end. In the very least, from the structural perspective, mass and satellite quenching seem to act in the same way. They may well be the same process. So I'm at checkout, and checkout I still 1 item in my basket, and the item is the evolution of the median size of the quenched population with cosmic time. Again, I focus on redshift smaller than 0, and this is something, please, that you have to keep in mind. Important, as has already been highlighted by several of us in the audience, several people here, that we count how many objects we have with different sizes. And at checkout, I don't have time to go into the detail. I want to show the plot that I was trying to describe yesterday in words. If you actually, between redshift 1 and redshift 0, construct the size function, which is what I was showing to you before, the moving number density of galaxies quenched with early type morphology of different sizes, and here color-coded are the redshift bins between 1 and 0.2 in the cosmos sample. And then you sort of take the ratio between what happens at late epochs and what happens at early epochs between redshift 0.2 and 0.1. This is what we obtain. So this is 1. It means that you don't lose any of the compact galaxies below half-life radius of about 2 kiloparsec. And where you get the increase in the quenched population since redshift 1 to today at a M star mass scale is actually at the large sizes. Now, this in its, so it's really a growth of the big population. This in its own can have any explanation, including merger and any other. But there is another important point of information that in the cosmos data is unequivocal. If you take the rest frame U minus V colors of these galaxies, and you now look at what the distribution of the compact quenched early type galaxies, the gray histogram does from redshift 1 to redshift 0.2, and what the large galaxies do from redshift 1 to redshift 0.2, what you see is that actually the colors, rest frame human V colors of the compact, become systematically redder as you come from redshift 1 to redshift 0.2. And if you compute how much they are redder, they're precisely redder of what you would expect from a passively evolving population. So I'm an experimentalist, I see this, and I say my working hypothesis at this point must be that this is a stable population that does not evolve in size and passively evolves since redshift 1. If we now compare the colors of the quenched large early type galaxies with the colors of this compact stable population, at any single redshift in any single of these quadrants here from redshift 1 to redshift 0.2, the distributions of the large ones, which is the distribution here hatched in black, is always bluer than the distribution of the compact quenched early type galaxies. And so at face value, if this is telling me something about ages of the population, then the larger galaxies are systematically younger than the compact galaxies, which leads to ansatz that what's happening actually is that you leave alone the compact objects since redshift 1 to today, and what you do is increase the median size of the global population by adding a later and later epoch larger and more diffuse quenched early type objects. How does this story relate, and why is it in my basket today? Because it's very neat. I can now go and do the size function evolution of the star-forming galaxies from cosmos, equivalent sample, equivalent mass. Note, please, that these are bulge-dominated, very high central densities in this population, so we're not quenching pure disks at this mass scales at these epochs, but dense systems. And let's quench these objects now, and let's see whether we can understand the size evolution that we are seeing there. No time to go into the trivia, but of course we can also predict how many of these star-forming galaxies should be quenched using, for example, the Peng et al. Prescription. And this prediction is actually the green histogram here. So the size function, what the size distribution of the just quenched out of the main sequence star-forming population should look like if we could observe it. And the black hatched histogram here shows the difference between the size function of the quench observed in cosmos, quench early type galaxies at early epochs, the gray histogram at redshift 1, and the size function of the quench early type galaxies at lower epochs at redshift 0.2. So this is the sort of histograms that the newly quenched early type galaxies would have if you quench the galaxies straight out as time, from the main sequence as time progresses in the universe. And of course there is a problem in these two distributions. Again, no need to quantify that. This arrow, the median is here, and the prediction from straight quenching of the star-forming galaxies is here. Yeah. So these are different. Do we have a problem? And this is where I connect in the basket the story, because the difference is 30%. And I've just shown to you that just sensible fading of the disks of the star-forming population absolutely can account for this. And so at this point in time, all this data since Redshift 1 really tell us that if we want to produce M-star spheroid, the only thing we have to do is to dump them dead from the star-forming main sequence down to the red and dead sequence as time progresses from larger and larger galaxies. This is indeed my summary, and I want to make sure that we all are on the same foot. I am talking about masses above 10 to the 10 solar masses, and I'm talking about redshifts lower than 1. I am the first one who actually thinks that things get different as you go to higher redshifts, and indeed Joanna is going to, I hope, talk about a little bit smaller masses, and Sandro about some thoughts and results at higher redshift. But at these masses and at these redshifts, then I won't repeat, because the chair is going to be politically incorrect with me, my 4 main points. But what I want to go to is one last consideration. I started with arguing that we should have 2 quenching processes because of the separability. And one of my points is that we have more or less the same quenching process given the way it acts on morphology. How do I reconcile this? And actually, I think it's pretty much reconcilable, because there is no need from the data and from the theory even to have 2 quenching processes. In particular, satellite quenching might well be the same as mass quenching if you link the satellite quenching to the parent halo of the satellite. And so if you really think of quenching as a halo quenching process, that I believe Avishai has been advocating for a long time. And this is totally supported by the data, even in a sense, in the Peng et al. To the return that we did, because indeed we do observe mass independence of the satellite quenching, the independence of the satellite mass function on the group halo mass, that therefore would give a complete mass independence of satellite quenching from halo mass that we observe. That's it. Thank you so much.
Just a few questions. Joanna, why don't you come up and start setting up? Yeah.
Okay, so this is a really nice rubric for how to analyze this kind of thoughtfully, so I really appreciate that. I agree entirely with the satellite quenching, that this is the fading of disks is often so. The early type fraction fading flat, but then the quench fraction going up, which is just telling you that disks are turning off, they're not turning into early types. I guess I'm not sold on the central quenching preserving structure. So one of the observations Jerome Fang and Edwin Chung emphasized that the central density within the central kiloparsec of the quenched population is substantially larger than the unquenched population, even in a given set of mass. And so I do think that that's telling you that dissipation has something to do with the quenching of central galaxies. Although I do want to kind of emphasize that all of these things, so that the one thing to ask about path spans is that even early type galaxies have color gradients. So they have color gradients that are almost as impressive as late types. And so I actually kind of, I think one has to think, this is a beautiful method. I think one has to even maybe go to stellar mass maps, which is grody. I hate stellar mass maps. But so I think it's the right way to think about it, and it's a good path. But I guess my question, what's your reaction to the work that suggests that the central density of the quenched galaxies, or centrally quenched galaxies, even at a given solar mass, are denser?
So this is a very interesting. By the way, Sandro will show later precisely the plot of central stellar mass density within 1 kiloparsec versus stellar mass, the redshift 0 using exactly the sample I'm moving on, and overplotting the redshift 2 population. One thing that I don't want to steal the thunder, but one thing is that this relationship is absolutely universal as you go out in redshift. And so one of the important things that I think is universal these days, again, the Sandro is about to talk about, is that indeed galaxies must grow for as long as they start forming. They must grow along the sequence. And so for as long as they are growing and growing universe, and it progresses toward the outskirts. And the universality of that relationship means that you grow the stellar mass at lower masses till you hit this saturation, sort of the stellar densities. I don't know if this is what you were asking. If not, better we'll talk later.
All right, one more very, very quick question. All right, back there.
I was just wondering with the satellite results, if you worry at all that the disks will actually be tightly stripped before the bulges, and so you can get a differential morphology bias just by the fact that you're selecting satellites.
So actually that would help, because what you're trying to argue is that you have to find a way of why you end up finding the scale lengths of the quench disks smaller than the performing satellite. So you add another reason why we shouldn't very naively just fade the disks as they are. So of course it's a complication in the picture, but the point is well made. We even have more reasons to think we can explain it all as affecting the disks rather than the center, rather than the bulges. Okay, so
Joanna?